So this is our warm-up. Let me turn my camera around so the mic works better. Okay. And what I gave you a little hint, and I said, remember the two formulas that we learned on Friday. I'm going to write each formula below one of these problems. So this one, I'm going to write the limit as x approaches a of f of x minus f of a over x minus a. Now, if you look at this formula and you look at this problem that's right above it, things kind of fall into place a little bit. So I don't know if you can tell, but since it's the limit as x approaches a, and I'm asking you, hey, x equals this is like our a right here, this blank, right? That's like the a.
Good morning again, EP. To continue our drills today, a duck and cover.
All right, so when you look at this form, you kind of line up and you say, all right, so f of x, that's my f of x. So if I want my f of x for this function would be 8 minus x cubed. Okay? All right. Now, my a, I've already said, was 5. Let's check and see if this makes sense, right? So that would be my f of x. F of a would be, in this case, f of 5, right? So if I plug in a 5, I get 8 minus 5 cubed. Does 8 minus 5 cubed equal 27? That's my f of a, right? So f of x minus f of a over x minus a. So f of x minus f of a over x minus a. So if you see something like this and you know this formula, can you pick out what's f of x? Can you pick out what's your a? The reason for this is because later on your AP exam, the College Board is going to give you limits like this. Now this one you could do. It's not short. You have to cube a binomial, right? Combine like terms, then you're going to have to do some factor, and then cancel, right? So you factor, you cancel. Once you've canceled, then you can plug in your 5 and you get an answer. If you recognize that this is slope with a tangent, which today we're going to learn a word for it, which is, anyone know what the word is? It starts with a D. Derivative, right? If you memorize hey, this looks like a derivative, if you know it's a derivative, then you can, starting on next week, Tuesday, we're going to learn really fast ways to find derivative, and you can save yourself 5 minutes of time by just going, oh, derivative, plug in a 5, done. You could do the limit, but knowing, if I can look at this, recognize it's a derivative, pull out the function, and pull out the value, I can save myself a lot of time. Now, this one's a little bit harder. It's the other formula. By the way, when you see the delta x, what can you replace the delta x with? H, right? So this is the same thing as h. All right, so we have the limit as h approaches 0 of f of a plus h minus f of a over h. That was the second formula we learned on Friday. This one's a little harder. It's not like there's just an in-your-face f of x kind of a thing, right? So instead, you have to kind of think about it a little bit. So let's start first and just look at the number we're talking about, the a value. So in this case, we're plugging a plus h into our function. So a is the number being added to h. So look at this. What do you think a is? 3, right? F of 3 plus h minus f of 3, there's your 3, right, over h. So for this one, our a is 3. F of x, that's the function you're plugging 3 into. So replace the 3 with an x, and you've got your f of x. Yes, very good. So f of x is the cube root of x, because that's what you're plugging your 3 into, or your 3 plus h into here. a little bit harder, but you can get there. Now, why would you really want to do it for this one? Because if you had to do this limit by hand, it's insane. All right? This limit on its own is crazy hard. So I will tell you, for fun, one year we were on a road trip, I remember. So I'm with my family, we're driving to Michigan. I'm not driving, I'm in the passenger seat and I have time to kill. And so I'm like, I'm just gonna see if I can do this limit without using the derivative, right? How would you do this limit? Do you rationalize? So would I multiply 3 plus h to the 2/3, right? Plus, I don't know, plus a to the 2/3? I don't know, 3 to the 2, I don't know. So I tried that and it didn't work. I read pages. I had so many pages of work trying to do this limit by hand. It was so crazy. And I finally gave up, and I'm like, well, it's a good thing we know it's a derivative. I remember saying that to my husband, who had no idea what to talk about. But anyway, I said, oh, it's a good thing I know this is a derivative. Now, you can use one method. Later on, you're going to learn something called L'Hopital. And then L'Hopital makes this one actually really easy. But without L'Hopital, this is a really crazy limit. So anyway, so being able to recognize this formula gives you slope of the tangent, or in other words, derivative. Being able to recognize, hey, this is a derivative. What's my function? What's my number? All right, I'm just going to find the derivative of the cube root of x at x equals 3, and I can be done in 15 seconds. Okay. So today we are going to put them together. So today we're learning the two formulas that we learned that we were calling slope of the tangent or instantaneous rate of change. Now we're going to call them derivative. So this is still slope of the tangent. It's still the instantaneous rate of change, but now we have a new notation called, and it's F with this apostrophe. I had to send you an email Friday night because this actually got introduced in your homework on Friday, so I apologize that I hadn't shown it to you. That F with an apostrophe, when we see F with an apostrophe, we say F prime. Anytime you see an apostrophe in math, it means you say prime. So when I see this, I say F prime of A. So it's not just F of A, it's F prime of A. It's like a shorthand notation for derivative. Same thing here. So there's no difference, it's just the other formula. So same thing again. So it's just your two formulas. They're just writing them out. So both of those give you what's called F prime of A, or the derivative of F of X at X equals A. So a derivative is a fancy word that means slope of the tangent line. It also means instantaneous rate of change. Everyone's writing. You have these formulas in your notes already, right? Okay. So there's nothing new. You're just calling it F prime instead of just the formula. Okay. All right, so we're going to start. We're going to do a couple of mathy problems and a couple of writing problems today. So today is a mix of some calculus-y, algebra-y stuff and then some writing stuff, because today we're going to learn how to explain stuff. So we're going to first find the derivative of f of x equals x squared minus 8x plus 9 at x equals 2. So finding the derivative is the same thing as asking you to find the slope of the tangent or the instantaneous rate of change. All those three things are synonymous, right? Derivative, slope of the tangent, instantaneous rate of change. They all mean the same thing. And they all mean you're going to use one of those two formulas you just learned. Now for this, it doesn't matter which formula you pick. They both work. I will tell you that the f of a plus h minus f of a over h, the h one, you'll be plugging in a plus h in for your x, so you'll have to like square a binomial, you have a bunch of like terms you'll have to combine, and then you like kind of clean it up, cancel the h's, and you'll be done. If you use the second one, f of x minus f of a over x minus a, then it's just a factoring problem, right? So if you like distributing, combining like terms, and canceling, go with this guy. If you like factoring, go with this guy. Right? Whichever one you prefer, doesn't matter to me, but see what you can do with this problem once you work on it. All right, let me unfreeze the board. Here we go. So we'll start with, can you please let Vivian, please? Thank you. Okay, so we're going to start with, by the way, shorthand notation for this would be f prime of 2. So if I want to give the answer a name, I would call it f prime of 2. F prime of 2. So the derivative of f of x at x equals 2 is written as f prime of 2. All right, so we'd have the limit as x approaches 2 of f of x minus f of 2. What's f of 2 when you plug in a 2? What do you get? -3. Is everyone okay with plugging in the 2? You get -3 over x minus 2. So just cleaning this up a little bit. X squared minus 8x plus 12. And then you factor. So you get x minus 6, x minus 2, 5. And then you plug in your 2 because we have canceled our common factors. And our answer is -4. How did that sit? Everyone I saw was okay, but I didn't get over to the back. Okay. All right. So I was asked to do this using the other definition because you might have to know both on your test. So let's just make sure, right? So if we do the limit as h approaches 0 of f of 2 plus h. So you're plugging in 2 plus h in for the x in your function. So you get 2 plus h squared. You're replacing your x's with a 2 plus h. So 2 plus h squared minus 8 times 2 plus h plus 9 minus, so f of 2 plus h minus f of 2, which we've already established is -3, all over h. Now it's just a whole bunch of algebra. All right, so let's square this out. So we get 4 plus 4h plus h squared minus 16 minus 8h plus 9 plus 3 all over h. Just distributing it all out. All right, I'm going to write this nicely in descending order. So h squared is h squared. I'm going to underline as I go. So h squared, done. All right, 4h minus 8h is -4h, right? Okay, goodbye, goodbye. 4 minus 16 is -12, plus 9 is -3, plus 3 is 0. Numbers are gone. All right, over h. Is that okay? Yeah? All right, good. All right, so now everything, if you did it right, everything without an h should cancel so that you can cancel an h from every term. We're left with h minus 4. Plug in a 0 for h, and what do you get? -4. It works. No way. All right. So anyway, personally, I think the first formula is a little bit easier. If I had a choice, I would go with that one, right? But if you are if you're not good with factoring, then this one, doesn't have factoring, right? But you do need to become good with factoring because there's a lot of factoring this year. All right, any questions on derivative, like using your formulas? It's just a repeat from Friday. Okay, little quick summary. So again, I'm going to say this, the derivative gives you the slope. The two main ones are the slope of the tangent and the instantaneous rate of change. The two main things that you need to know is that the derivative gives you the slope of the tangent line, which is the same thing as the instantaneous rate of change. Now, the book really emphasizes motion a lot. So they included in their summary, so I included it. They included, hey, if your function represents position, then the derivative gives you instantaneous velocity. All right? If the function represents position, then the derivative gives you instantaneous velocity. But the main things, like this is more an application. These two they're like generic. They go with anything. Doesn't matter what the function is. No matter what your function represents in the world, the derivative gives you the slope of the tangent line, right? The line tangent to f of x at x equals a. It gives you the instantaneous rate of change of your function at x equals a. So those two things are key. All right. We're going to use this knowledge to do some interpreting. Yay. That's right, yay. Okay, so we're going to do a cost function. This involves writing. I would write this, all right? So if you don't normally write, you will have to learn how to write. This will be ongoing, like all year. You're going to have to answer questions that say, explain the meaning of, and it helps if you know how to do it. There's kind of a formula way to do it. Part B is more important than Part A. They're both important, but for what you will be doing more often this year is Part B. But we're going to do both, just so you understand both. All right, so the problem says a manufacturer produces bolts of fabric with a fixed width. The cost of producing X yards of this fabric is C equals f of x dollars. So our function is, I'm not going to tell you. I'm going to wait for you to write, and then I'm going to ask you. So let's just look at Part A. What is the meaning of the derivative f prime of x, and what are its units? Are you okay? Are your eyes, like, do I need to move you? All right, so on the previous page, we said the derivative gives you slope of the tangent, instantaneous velocity, or instantaneous rate of change of a function. Of those three, which one do you think would be most appropriate to use in our description here? Instantaneous rate of change. Slope of the tangent would be if we're just literally talking about a graph and a function without a lot of context, then we would talk about slope of the tangent. But since we have context and meaning, we're going to talk about our derivative as an instantaneous rate of change. So, what is the meaning of the derivative f prime of x? F prime of x represents, and I'm going to write this all out, no abbreviations, just so you get the whole thing, represents the instantaneous rate of change of, all right, what does our function represent in the context of this problem? What is it?
Yards over dollars.
Okay, that would be what the rate of change represents kind of. All I'm asking is for our f of x, just our function. What does our actual function represent, the f of x? It represents cost. It's production cost, right? It's the cost of manufacturing X yards of fabric, right? So f prime of x represents the instantaneous rate of change of f of x. What is f of x? The cost of production, rate of change of the cost of manufacturing or producing X yards of fabric. So the cost is in dollars. So the output, our function, is in dollars. Our input is in yards. So if I ask the units for f prime, units for f prime, what do you think it would be? Dollars over yard, dollars per yard, dollars per yard. It's just like slope. Change in y over change in x, it's the units of y over the units of x. So in this case, it's the units of cost, because that's what our y is, so dollars over the units of our x, which is yards, right? So the units for f prime would be dollars per yard. If f is in dollars and x is in yards, then f prime is dollars per yard. It's slope. Rate of change. Okay, now the more important one, I'm going to put a big star by B. Because B, you're going to get asked a lot more often. You're going to be asked to explain with numbers way more often than just with generic functions. So in practical terms, what does it mean to say that f prime of 1,000 equals 9? There are things that students get right about these every time and things that many students miss every time. If you follow what I show you right now, you'll always get these right. But you have to be careful because there's such a common mistake on these, and you're going to want to fight it and say, I put it, and I'm going to say you didn't, not for this. So hear my voice when I show you what to do, follow it. Learn this and just have this stick in your head every time. When you have to explain a meaning of a derivative with numbers, you always start with the input first. Don't jump in and try to talk about what a derivative is. You always start with the input first. Our input in this problem is x, right? And x represents yards. How many yards have we got in this problem? Is it 1,000 or is it 9? It's 1,000. It's your input. It's what you're plugging into your function, right? So here's how you write this. When 1,000 yards of fabric are produced. So you start with the produced. All right? Always start with the input and include the units for the input. All right, a lot of people like to say, hey, when x equals 1,000, the whatever is whatever. X equals 1,000 doesn't say anything about the meaning of the input. You have to describe the input with units. You got to describe the input with units or you're not going to get credit for your answer. All right, input with units and then derivative with units. It's got to have input and output. All right, so next, when 1,000 yards of fabric are produced. Okay, next you write, what does your function represent? What does the f of x represent again? The cost of production, right? Okay, the cost of production. Whatever the function represents goes here, and then all the rest of the words are the same for every single one of these problems until you die, all right? So you write your input, you write what the function represents, And now from here forward, these words never change, except like maybe with the numbers, but not the words. So when 1,000 yards of fabric are produced, the cost of production, here we go, is changing at a rate of. So this is your Y. The changing at a rate of is what makes it a derivative. All right. Now, we said f prime of 1,000 is 9. 9 is not a Y value. It's a derivative value. It's the rate of change, right? So don't confuse. It doesn't say f of 1,000 is 9. It says f prime of 1,000 is 9. This is a derivative. So the cost of production is changing at a rate of 9. And then what are our units for this derivative? Dollars per yard. Dollars per yard. So it's your f prime value with units. So input value with units, say what the output represents, changing at a rate of, derivative value with units. So f prime of 1,000 equals 9 in this problem says, hey, when we produce 1,000 yards of fabric, our cost of production is changing at a rate of $9 per yard, which means is the cost of production increasing or decreasing at that moment? It's increasing. It's actually becoming more expensive to produce more fabric, right? The more fabric we have to add onto that bowl, the higher the cost of production becomes. All right. We're going to talk about this in just a second. Okay. All right. I want to change this problem a little bit. It's one that I made up. It's very poorly worded. And I'm going to add a table value to it. All right. So instead of having this be over an interval, this represents heat 8 at 1 p.m. All right. So here's the thing. There are some kind of, you have to take, this is a handwritten problem and it's not very good. But it'll help with a few ideas that we need to learn. And we're just going to go with it. So it is kind of an interval, but I want to kind of think of it as an endpoint. So the table to the right represents the number of jelly beans Mrs. Price's son Daniel consumed each hour starting at noon. So x equals 1 represents 1 p.m. And f of 1 would be how many jelly beans he ate at 1 p.m. Now, for purposes of this problem, let's just say he didn't eat any in between. So at 1 p.m., a timer went off and he threw 30 jelly beans into his mouth and swallowed them. Okay? Okay. All right. Then at 2 p.m., 80 jelly beans went in. You know, you haven't seen my son Daniel, he could do it. All right. Okay, 3 p.m., 50 more jelly beans, right? 4 p.m., he was probably sick then, he didn't eat any, right? 5 p.m., he managed to get 10 more down. Okay. All right. So my first question to you is how many jelly beans did he eat from noon to 5? So what do you think we should do? Add them together. So everyone take a minute, find how many jelly beans he ate from noon to 5. No calculators. Oh, that was fast. You guys can add fast.
Yeah.
Okay. If I left my answer like this, would I get full credit?
Yes.
Yes. Right? Absolutely.
Yeah.
Oh, he ate. There we go. He ate. He ate and he ate. Okay. So if you got an actual answer, just so you know, you got the answer was 170, but you can leave it unsimplified. Unsimplified is fine. Right? Unless on the test or whatever we specifically say to simplify, unsimplified is fine. What was Daniel's average rate of jelly bean consumption from noon to 5. Average rate of change. What does that make you think of when you have to compute an average rate of change? Slope of the secant. Slope of the secant, right? Instantaneous is slope of the tangent. Average is slope of the secant. Slope of the secant is just old-fashioned slope, right? It's just change in y over change in x. We are finding the average rate of change from time 0 to time 5. Take a moment, see if you can find the average rate of change from time 0 to time 5. Yep, from noon to 5. So from 0 to 5. Noon to 0.
Like 0 minus 5. No, it's
Yeah.
yeah, but that's not 2 beans per hour.
All right, let's talk about what average rate of change means. F of 5 minus f of 0 over 5 minus 0. What's f of 5? 10. What's f of 0? Over 5 minus 0. Our average rate of change is 2 jelly beans per hour. Average rate of change, 2 jelly beans per hour. Now, that actually is not true because technically what I should have done with this table is done a cumulative number, not the number at that hour, right? So technically this is nonsense because technically for this to actually have any meaning in context, this should be 30, this should be 110, this should be 160, this should be 170, and then your average rate of change would be 170 divided by 5, and it would make sense, right? You guys get that? Okay. So for an average rate of change, really this needs to be cumulative. I told you it was a bad problem, okay? But anyway, either way, what I'm really driving at is can you do the math? So do you understand how to find an average rate of change even with nonsense numbers? Yes, okay, good. By the way, average rates of change don't always indicate what happened, right? For example, if I ran 20 miles on a track, all right, and say it's a circular track, I run 20 miles. Say it takes me, I don't know, like 5 hours, right? Okay, so if I run 20 miles over 5 hours on a track, and I end at the starting line, what was my average velocity? 0, because I had no change in position. My ending position was the same as my starting position, which was 0. So my average velocity, 0. Does it mean that I didn't have any velocity in there? Of course not. That's the thing about average velocity or average rates of change. It's just ending minus starting, and it doesn't take into account what happens in the middle. Do you understand that? Okay. So sometimes the numbers for average rate of change seem like nonsense, but they are what they are. But you were right. For this one, it is nonsense. Okay, good. Good call. So I told you it was a bad problem. Go on. All right. So number 3. We're going to estimate f prime. We're going to use the bad numbers. That's okay. We're going to go ahead and use them and estimate f prime. So f prime of 3, when you have to estimate a derivative from a table, you did this. It was our first homework assignment. You were asked to estimate slopes of tangents a whole bunch of times. And so in that first homework assignment, right, we're interested in 3. The book would have you do the slope from 2 to 3, and then the slope from 3 to 4, and then average them together. Does that kind of ring a bell? Okay. On your test or the AP exam or future tests or whatever you're doing in this class, the College Board will accept that, but the method that they promote, which is the one that I like, which is much, much easier, is not that. So the method that they promote is you find where you want the derivative, you go down one, you go up one, and you do the slope of the secant that connects those 2 points. So this one, those two. Just go up one and down one from where you want the derivative and just do slope of the secant. And then you're done. You don't have to find multiple slopes and average them. You just slope from 2 to 4. Do you understand that? Okay. All right. So for this, okay, there's 2, there's 4. So we'd have f of 4 minus f of 2, 4 minus 2. F of 4 is 0. F of 2 is 80 over 2. Negative 40. Now, does that mean he's vomiting the jelly beans? No. It just means that his rate's going down. So the number he's eating is decreasing, right? Okay. All right. So the number of jelly beans he's consuming is going down at a rate roughly of 40 per hour, like 40 less jelly beans each hour, right? Does that make sense? Yeah, it's not close, but it's somewhat relative to what it would actually be. All right, around 3 p.m., is his rate of jelly bean consumption increasing or decreasing?
Decreasing.
It's decreasing. We don't, actually we do know this for sure because I said he doesn't eat anything in between. Now, normally when you have a table, if this was a legit table, and say you only got what he was eating at that moment, but you didn't know what else he was eating in between, then you wouldn't know because for all you know, at 3:05 he could eat another 122, right? But because I told you that nothing happens in between, then you know, right? So tables are mysteries because we don't know what's happening in between the values. All right, moving on. That is all I want to spend on that one. This one, this is your challenge problem for the day. Do you guys like to be challenged?
Yeah.
Good. Okay. This is your challenge problem for the day. It is not a challenge. Most of the time I like you to be challenged mentally. This one is challenging algebraically. It's challenging algebraically, but I think you can do it. So here's the thing. You have to find the derivative without any numbers. So instead of finding the derivative at x equals 2, you're finding the derivative at x equals a. So instead of putting in a number, you're just going to use the letter a. You can use either definition. Either definition. So neither one of them is like super easy. But I will tell you, we did the f of x minus f of a over x minus a one in first period, and it worked pretty well. So I will probably do that again when I explain it. But you can use either one. You could do the h approaching 0, 1, 2. Whichever one floats your boat. So I'm going to give you I have to unfreeze. Unfreeze. So which method did you guys use?
The first one.
The f of x minus f of a over x minus a? Yes, the a one, not the h approaching 0, 1.
Yeah.
You could do either one. But you like the a one?
Yeah.
I know. That's the one I like better too. And I don't mean to imply like a personal preference for one method over the other. They're both perfectly valid methods. I personally just find that one a little bit easier. So, all right. So we have, so I'm going to rewrite f prime of a is the limit as x approaches a of f of x minus f of a over x minus a. Most important thing you could do in these problems is set it up properly. So how did we do it on set up? Thumbs up, thumbs down, thumbs up, okay? All right, so we got the setup. All right, now we get to do some algebra. So we have to multiply the top and bottom by the conjugate. So I'm going to put it over here in parentheses. Since we have these radicals, it's the only thing to do. All right, multiplying top and bottom by the conjugate. So we get, rewrite your limits, don't forget it. Root 2x minus 5 times root 2x minus 5 is 2x minus 5. Minus, make sure you subtract the quantity, right? Root 2a minus 5 times root 2a minus 5 is 2a minus 5. All over. Should I distribute this out?
No.
No. You never distribute out the denominator. All right. It's not awful. This isn't bad at all, right? So now we just combine some like terms on top. So 2x is 2x minus 2a. Now we have negative 5 plus 5, so those are gone. All right. How are we so far? How are you doing? Oh, Faith gave me a big thumbs up. Awesome. All right. Faith's on track. Here we go. Faith, what do I need to do now?
You can take the 2 out of the x minus 7 and cancel out the x.
Beautiful. So these two are gone. Once you cancel, you can plug in, right? Don't leave it like this. You got to actually evaluate the limit. The whole point of doing all this was to evaluate the limit, right? So when you're done evaluating the limit, there shouldn't be any LIMs anymore because you've found the limit. It's whatever you get. So when we plug in, as x approaches a, we plug in an a for x, not an x for a, an a for x. So we have 2 on top, and on the bottom we have root 2a minus 5 plus root 2a minus 5. Now if you simplify this, you get 2a minus 5 roots, and you can cancel the 2's, and you're left with 1 over root 2a minus 5. All right, I am so curious how many got there. Look at you guys, you're like superstars. Well done. Now, if you didn't get there, it doesn't mean you're not a superstar, right? It just means that this problem got you stuck somewhere. So front groups, where did you guys, what got you stuck?
What? Oh, we just didn't evaluate plugging in.
Oh, so you got really close. You did all the hard stuff. Okay, good. Well done. All right, so yeah, you got all the way to here and just didn't plug it in. All right, good job. All right, are there any questions? That was a pretty tough one. Now let's talk about what this means for a minute before we move on to the last problem and talk about your homework. So why would we do this? Why would we want to find a derivative with no numbers? What would be the benefit? Faith, what's the benefit?
If you have to do the derivative of multiple numbers.
Beautiful. Yeah. If I asked you to find f prime of 2, f prime of 3, f prime of 5, and f prime of negative 27, right? You would not want to have to do 4 limits, right? All involving rationalizing 4 separate problems. So instead, you do 1 problem, right? Just keep A, and then what can you do? You get to the end, and then you just plug your numbers in there, bam, 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 and then you've got the derivative at all 4 spots. Does that make sense? So this actually has a name. We're going to talk about this tomorrow, not today. You don't have to write it down. But this is actually called a general derivative. And what it means is this is like a function that gives you the derivative at any spot. You plug in whatever number you want, and you get out the derivative. Okay. All right. So our last slide, I want you to think about, if I asked you to give me 1 word, not 3 words, 1 word that represents derivative, 1 word that is a word that tells you a derivative. Like a derivative gives you what in 1 word? What would that word be?
Slope.
Very good. Derivative gives you slope, right? Okay. So if a derivative gives you slope, I have 2 graphs up here. All right, this is number 1, this lovely parabolic curve here. This is number 2. You've got a linear function and another linear function. Kind of looks like an absolute value. Who knows, right? Okay, so I have 2 functions here. Down here, I have 4 derivative graphs. Your job as a group is to figure out which derivative goes with each function, all right? And remember, your keyword is slope. The derivative gives you the slope, all right? Do we want to put the answers on our whiteboards? Yes?
Sure.
Yeah, I think I want to see them. All right, you don't have to write a lot. All I want to see is a 1 with a letter and a 2 with a letter, okay? That's all I want to see.
But that doesn't, wait, sorry, no, it makes sense.
Oh, okay. All right, are you ready, set, go?
It's 1 and 1.
It's 2.
All right, so here's the thing to know about number 1. Tell me one thing that I know about the slope of this half of the graph. Tell me, Zuhair, what's one thing I know about the slope of that half?
Everything's negative.
That's what I'm looking for. The slope is negative because the graph's going down, right? Okay, so we know that whatever our derivative is, it has to be negative on this half because the slopes are negative. Does that make sense? This graph's going down. And then for this half, our slopes have to be positive because it's going up, right? Now, don't confuse negative with decreasing. Negative just means below the x-axis. It means literally negative. Are the numbers, if I plugged in a number on this side of the y-axis, would I get out a negative value on the derivative? So that's why it goes with D, because our slopes are negative to the left and they're positive to the right. Now, Zuhair was saying that the slopes approach infinity. They do on the ends, right? If we're talking about the ends, like this way and this way, this way and this way, you're right. The function's getting steeper and steeper and the slopes do approach infinity. At 0, what does it look like the slope of the tangent is at 0? It's 0, it's horizontal, right? So what we've got is a slope of negative infinity, and then the slopes get mathematically bigger, numerically bigger, even though like slope-wise we think of them as getting smaller, like -4 versus -2 versus -0.5. So you think of it as getting shallower, even though numerically they're getting bigger, right? So anyway, so we go negative infinity towards 0 and then 0 towards infinity. And that's why you have this guy that has, as x approaches negative infinity, the slopes approach negative infinity. As x approaches 0, the slopes are 0. As x approaches positive infinity, the slopes are approaching positive infinity, right? And they're always changing, right? People get confused between the graph of the derivative and the original function. And they look at the derivative and they're saying, but wait a minute, it's a linear. This means constant. No, that would be the slope of the slope, right? These are changing slopes because remember this graph is a graph of slopes. What is the slope at -1? It's the y value at -1. Okay. All right, so this guy, absolute value, no matter where you are on left of the y-axis, what's the slope? -1, it's a constant, right? Because it's a line. To the right of the y-axis, what's the slope? 1. It's also a constant. So we need a function that is a constant of -1 and then a constant of 1. And that's why you get C. Now, we're going to talk about this tomorrow, but just a little note. If I asked you the slope of the tangent at 0, would you be able to give me one? There isn't one. You can't give me one. How would you draw a line tangent, right? If you define tangent as only passing through one point, there's infinitely many. But if you define tangent properly as sharing the same slope, there's none. Why are there none? Because to the left, the slope is -1. To the right, the slope is 1. So at that point, which one does it pick? It doesn't know. right? It can't. So it's just stuck. So at 0, there is no slope, technically. It's undefined. All right, good. So let me show you, that's it here into the lesson. So let me show you, I need to show you something about last Friday's homework.